First, let's take a look at NetOps from an introductory perspective. In this section, I'll discuss why NetOps is important, how do we improve it, what is NetBrain, what is the NetBrain NetOps certification program, and then I'll wrap things up with a discussion of the 4 pillars I focus on when looking at network operations and the methodologies that NetBrain has developed to support the different pillars. First and foremost, we need to understand why NetOps. NetOps is a short form for network operations, and virtually any discussion surrounding NetOps will have one of 2 goals in mind. The first is to increase availability, and the second is to reduce mean time to repair. As we go through this program, please keep these goals in the back of your mind. This will help deepen your understanding of the concepts that we'll discuss, allowing you to better retain the information, and then measure against your current practices, and lastly, implement NetBrain in some of the targeted areas that will help you meet the goals of NetOps. In order to understand the 2 overall goals, I wanted to take a moment to help define availability and mean time to repair, which is also known as MTTR. So we're on the same page. Availability is simply the percentage of time the network is available to the users, and it's represented in percentage. When I think of availability, there are 2 areas that a NetOps engineer should focus on to ensure high availability. These are network redundancy and resiliency. While network resiliency and redundancy is typically owned by an architecture or design team, NetOps teams are often leveraged to provide feedback based on their interaction with the deployed network and the customers or users of the network. The best way that I've seen NetOps positively impact the process is to maintain up-to-date documentation. This increases the visibility of the network and, if the relevant documentation is maintained, allows the design and architecture teams to pinpoint potential redundancy and resiliency issues before they result in an outage to the users of the networks. When I look at redundancy, I'm most often looking at single points of failure in the network. This is where VRRP, BFD, fast reroute, VPC, port channels or lags, and ECMP will often come into play. So if a single link or a device fails, is the network redundant enough to ensure that the user does not experience loss of data that cannot be covered through TCP or application layer retransmissions? Again, having proper network documentation allows NetOps and design teams to visually pinpoint these single points of failures. When I look at resiliency in the network, I'm most often concerned with hardware and software and its ability to withstand a single element failure and continue to deliver uninterrupted service to the user. Over the last few years, there have been some interesting strides made by various vendors to modularize their software, for example. This way, if a specific portion of the software needs to be updated, only that single module of software needs to be updated while everything else stays in service. This is different than, say, the legacy approach of requiring a full OS upgrade that requires a reboot of the system. That reboot of the system would most often result in full device outages of 5 minutes or so, and without proper redundancy, extended outages to the user would occur. We also see a trend towards the virtualization of 2 or more physical devices into a single logical device. This allows physical connections to be made to both devices, have the connections bonded in some way, and then both chassis administered by a control processor in either of the 2 physical devices. In essence, this offers a 1-2 punch of resiliency and redundancy. If the control processor in one device fails, the other takes over. If the entire chassis fails, traffic can be handled by the other physical chassis. More traditionally, resiliency is often covered by things like multiple power supplies connected to different UPS protected power, multiple control processors inside a single chassis that can control the entire chassis should one of these fail. And while the control processor is swapping over, the chassis continues to forward traffic based on the latest information in the hardware forwarding tables, so the user may never notice a failure at all. Terms like nonstop forwarding, nonstop routing, graceful restart, and in-service upgrade all deal with resiliency. What's important to note here is that a detailed inventory of the hardware and software running in each element must be known to properly assess resiliency across the entire network, since this requires knowledge of the types of line cards, modules, number of control processors, and the software features included to enable this resiliency. The formula for deriving the network availability is as follows: total time minus outage time divided by the total time. Now, it's important to discuss the details of this formula a little bit more and also its application. First, the most common way to report the availability number is not per user, it is across the entire network. As we'll see in the next slide, there's a maximum amount of time that a network can be unavailable in order to meet a specific guideline percentage number. If NetOps managers focus on a per user number, then it will be virtually impossible to consistently achieve the most common target for availability of 99.999%. For this reason, almost all availability numbers are actually an average availability of all the individual users of the network. In essence, the total time is the total time in the sample size multiplied by the total number of end users. Secondly, when a network undergoes a change in what is called a maintenance window, this time is removed from the total time calculation. The reason NetOps managers can do this is that networks will have a weekly scheduled maintenance window during an off-peak time with every effort taken through the redundancy of the network to mitigate any impact to the users. In some cases, it is impossible to eliminate the outage. Therefore, proper communication to customers is required to ensure that their expectations are set correctly. With a little pruning of the total time variable in the equation, the focus will primarily be on the amount of outage time in the network. This leads to my next topic and probably the most important metric to track in a network, and that is mean time to repair. In summary, MTTR is the average time it takes a network operator to restore service in the event of an outage. It is reported in hours and minutes, and unlike availability, this number is heavily dependent on the people that operate the network and the processes that govern how they operate the network. The two areas that NetOps engineers and managers can focus on to help improve MTTR are automation and collaboration. The formula to determine MTTR is total downtime divided by the number of outages. Both of these numbers are very important to a NetOps engineer and manager in that in order to improve MTTR, we must reduce the total downtime or reduce the number of outages that occur. Let's dive a little further into availability. As you can see, once the availability number is calculated, trying to achieve 5 nines or 99.999% availability means that the network can only accumulate 5.2 minutes of outage per year. This is commonly referred to as carrier grade and is the ultimate goal of most NetOps managers. As a side note, if you measure the time to reboot almost any router in the market today, it will take less than 5 minutes from start to finish. Now that we know that carrier grade is the goal, vendors ensuring that a device reboots in less than 5 minutes ensures that a device reboot does not tip the availability scale in a way that misses the target of 99.99% and that the blame is not on the equipment vendor. If you look at your own network, you'll definitely have experienced times where just getting the ticket into the system takes longer than 5 minutes to document. Never mind replacing a cable or swapping an optical interface. Even 4 nines is virtually impossible to achieve from an individual customer basis. So with the averaging of availability across all the users and removing maintenance window outages from the outage time, the end users of a network could not use this number as a measure of their personal availability. This led to a customer-specific service level agreement, and without coincidence, the standard SLA is based on a 3 nines calculation, which allows just over 8 hours of outage per year. This is the most common SLA I've seen across 22 years in this industry without having to pay an exorbitant fee for the service, and is a target that was originally believed to be achievable if the provider focused on redundancy and resiliency. From the NetOps perspective, redundancy and resiliency allow us to, in some sense, hide outages from the customer. This follows the idea of if a tree falls in the forest and nobody is there, does it make a sound? In network speak, if a device fails in my network and nobody experiences an outage, does anyone care? Who does care are the NetOps engineers in that most often networks are built with the redundancy and resiliency level that can support 1 failure without an impact to service. Trying to design for more than 2 failures in the case of a system becomes extremely difficult, time-consuming, very expensive, and in some cases simply impossible. What NetOps managers quickly came to realize is that there is a point of diminishing returns, and no matter how redundant and resilient the network was made, there inevitably were going to be outages. What NetOps managers needed to focus their efforts on were people and process. Since there were inevitably going to be outages, people and process became the focal point to reduce mean time to repair. For example, if the first level engineer working on an issue does not know what MPLS is, then it becomes impossible to troubleshoot with the current set of tools on the market. Next, if the engineer does not know who to route the problem to when it is an MPLS related issue, this can stall the process even further. Maybe they route the ticket to the security team or simply skip over the ticket and leave it in the queue. Even more elementary than this, what if the engineer doesn't even know the username or password to access the devices to perform some data mining and analysis to determine that it is an MPLS issue? There are many process issues that I'm sure you can think of examples of as well. Another one that jumps to my mind that I've experienced multiple times in the past is the lack of knowledge of the SLA and contract details for a vendor or service provider. For example, what if an engineer believes that they have support on a device and they don't? What if you don't know which number to call or the login credentials to create a ticket with a specific vendor or supplier? What if you have gold level of service and are allowed to escalate specific issues directly to a second or third level of support and the ticket is stuck at level 1 with no activity for an hour? Again, there are many examples and I'm sure you can think of more and have probably experienced some of these already in your life in the NetOps world. Every second counts, so having highly enabled people with the right tools who know the process is really the only way to improve MTTR. So this leads to the question, how do we improve NetOps? It's relatively simple from a theoretical perspective. First, we need to improve visibility through relevant documentation, and then improve operator efficiency through automation. Relevant documentation allows NetOps engineers, as well as designers and architects, to perform redundancy and resiliency analysis. This truly speaks to what is often referred to as being proactive, or in this case, proactive NetOps. To do this, we need detailed inventory and asset reports of the networking devices and things like OS version, power supplies, control, processors, line card serial and model numbers, etc., etc. These all allow the NetOps engineer to identify potential hardware and software related risks and avoid any outages that these may cause. Secondly, current maps and diagrams on the network. Not just physical connectivity at layer 3, but layer 2, routing design, default route propagation, etc., etc. All of these improve the visibility of single points of failures and improve the understanding of the actual network and even the historical state of the network. Improving operator efficiency through automation includes things like automated path mapping. This is one of my favorite ways to improve efficiency. What I've spent many years working with are what I call all-purpose documentation sets that, while very extensive in their nature, are often not relevant to an issue that I'm working on at that time. First, most of these documents are out of date, so it can cause NetOps engineers to look in places that aren't relevant. And secondly, most of these are overwhelming in that they try to cover the entire site or function of the network. There could be 50 to 100 devices on a single diagram, so finding the devices that are relevant to the task at hand becomes very inefficient. Improving efficiency can also be attained by automating the data mining and analysis process. Today, these two functions are performed manually through CLI sessions or a graphical user interface and in a very serial way. The output of the data is analyzed manually as well, which is prone to error and can simply take a long time. Even more so, the data mining analysis may only be capable by a top-level engineer who has the domain and how-to knowledge to perform those tasks. Lastly, with the advent of powerful search engines for internet browsing, having the ability to search for relevant data on the internet has been a huge time saver. Applying the same concept to network data, it would be extremely helpful to be able to search for the data in your network, like where is a device with a specific MAC address connected? What commands have been run against a particular device in the past? Which devices in my networks belong to OSPF Area 0 or have a specific static route applied to them? Doing so removes Control-F type data searches across different data sets that may be available if you can find the location of the files you want to search in. What I hope that you've noticed by now is that a lot of NetOps topics are intertwined. Availability is impacted by MTTR. Operator efficiency, which impacts MTTR, is dependent on relevant documentation. Network documentation impacts the redundancy and resiliency of the network, which returns back to MTTR. Automated path mapping can be used to improve the resiliency of a specific application, and so on. This leads to the question, how do I accomplish these relevancy and efficiency topics, which is a great segue to the next topic. What is NetBrain? The easiest way to understand what NetBrain is will be to draw a comparison to a computer operating system. Each computer system has peripherals like a mouse, keyboard, monitor, webcam, etc., which, much like a network, is built from a set of components such as routers, switches, and load balancers. In the case of a computer system, vendors write drivers that enable input and output to and from the devices. In the case of the network, vendors provide CLI and API to the devices to push and pull information from the network components. Now, if we focus on the computer system for a moment, we know that there are many popular OSs out there, such as OS X, Windows, and a variety of Unix flavors. For the most part, from a user interaction with the computer system and the peripherals, we don't access them directly using the native drivers that were written for the application. We have some form of user interface. For the most part, it's a graphical one. As we move the mouse around, so does the pointer on the screen. In the background, the user interface is communicating with the mouse for directional data and with the monitor to draw the mouse arrow on the screen. This communication is very likely to be different for different models of monitors or mouse that you use. Regardless, in a computer OS, the result is always the same. On top of this user interface, companies write applications to amplify the user's ability to accomplish different tasks. Things like video conferencing, messaging, calendars, mail utilities, web browsers, office utilities, etc. Now we have an application that may be interacting with the mouse, keyboard, monitor, CPU, network card, local and remote storage, remote computer, etc. It would be simply too inefficient to interface directly with each of these components in a serial fashion, and in the native language of the many drivers for all the different vendors of each specific component, and still have the desired result of amplifying the user's ability to accomplish the task at hand. This is the whole purpose of the OS. Regardless of the underlying components, the user can have the same experience. Move the mouse, and whatever vendor mouse it is, it moves the indicator on whatever monitor I use. It is to the point today that most people don't even consider the complexity that lies underneath what they are doing, unless you're in the NetOps world and deal with this complexity on a day-to-day basis. Stop for a moment to consider every network vendor that is in the market today and how they all display outputs in a somewhat familiar fashion, but not exactly the same. How about the commands that they use to retrieve the data? In a lot of cases, this is the most dissimilar. Even consider Cisco as a networking giant. They have 4 major OSs in the products families that they have: iOS, iOS XE, iOS XR, and Nexus OS. Each one unique in their own way, requiring a different way to input and output data, much like the different vendors of a mouse, keyboard, and monitor, etc. require different command structures to interface with the peripheral. NetBrain has spent years addressing this inefficiency and created the total OS of the network. Now, just like Windows or OS X, NetOps engineers have a user interface which is based on a dynamic map, and once the map is created as the interface, NetBrain leverages device drivers to interact with the network components to simplify the user interaction. If you want to see the routing table for a specific device, click a button and the routing table is shown. Regardless of the type of device, you see it the same way. On top of this, just like computer OS, NetBrain and different vendors can create applications, we call them QApps, to amplify the user's ability to accomplish tasks. These are how we create custom automation, and to do so, you won't need to learn Python, Perl, or C++. NetBrain includes 100+ apps and has even gone to the extent of creating some embedded apps like a traffic path calculator, which automates the mapping of a layer 2 to 4 path through the network across multiple vendors, product families, and then includes highlighting functions that we can draw things like default route propagation and routing protocol topologies. As a driver for a device is created, so are the embedded functions enabled. From a QApp perspective, they can be customized to support any device that NetBrain can log into, and again, without any scripting knowledge required. How powerful is that? I spent 22 years in the network business, and once I saw NetBrain, I was hooked. I honestly don't understand how we've lived this long without it, but luckily for all of us, we don't have to any longer. NetOps models and methodologies. While there are many ways that NetOps impacts a business, including preserving the company's reputation and increasing satisfaction of the network users, most companies are very focused on the financial implications of outages. The studies presented here were conducted from 2009 to 2011, so it's easy to imagine that the numbers presented here are significantly higher in today's day. First is that operator error is the third top root cause for unplanned outages. And secondly, 63% of organizations feel that they don't have the resources to deal with these unplanned outages. The same study also reported that its respondents believed that after postmortem exercises, 45% of the outages were considered avoidable. If taken very literally, the root cause for the majority of issues would be labeled as a staffing issue. The fact of the matter is that since the burst of the tech bubble in the early 2000s, companies have been running their NetOps organizations as lean as possible. The challenge has been planning for the unplanned, which is where the NetOps teams have been struggling. Once activities are outside a small deviation from the norm, the process breaks down, overwhelming the team to the point where they feel they cannot keep up. Any survival training will tell you to be prepared for the unexpected. This is where we need to leverage the domain knowledge in our companies and the how-to knowledge of our experts to plan accordingly. As you'll see later in this section, there are definitely some resource challenges that exist based on current organizational structures. However, this is where the NetBrain platform can truly help network operators. While these 3 bullet points are alarming, they are often not enough to influence a change that will cost some upfront dollars to improve the overall health of the NetOps team. Most companies can deal with moments of chaos as long as it doesn't impact the bottom line financially. In this IDC report, 30% of respondents estimated that they lost $50,000 or more per hour of outage. Imagine a retail outlet like eBay or Amazon, Alibaba, or a large chain store in one of the major shopping holiday events. They could easily experience a loss in the tens of millions of dollars per hour. If people can't get what they want from one online site, they will go to another site. Even more potent is a financial trading company, who are very often concerned with milliseconds of latency across the network to make the best trade. An outage in the hours could result in hundreds of millions of dollars in loss, and as we've seen in the recent past, even closing of an entire stock exchange based on an outage impacting all traders, which have impacted numerous trading companies and publicly traded companies for something that had absolutely nothing to do with them. While there are extremes to everything, what I find very interesting is that 70% of the respondents to this survey, in particular, lost over $10,000 per hour. With SLAs in the 4 to 8 hour range, that is $40,000 to $80,000 of potential lost revenue. If we look to a purely sales-focused company, for example, while we would typically measure in the losses per hour, losing network access could result in missing a deadline to respond to a request for purchase, for example, or other time-related sales function, resulting in the loss of a sale, which could lead to personal financial strain. Also, since networks are ubiquitous now, every company in the modern world relies heavily on the network and the attached application to perform many of their core functions. Without them, business grinds to a halt, employee satisfaction is lowered, and company reputations can be hurt. All of these might be outside of the immediate cost per hour losses, but can have long-standing impacts to productivity and staffing. Over the last 22 years, I've had the opportunity to work with many different operations, design, and architecture teams. And through this experience, there were 4 areas that I determined were the pillars of a strong NetOps organization. Organizations that had people, products, and processes to address the 4 areas were much more agile in their ability to deal with the unplanned outages, reduce the number of planned outages, and had much happier employees at the end of the day. Ironically enough, the acronym spells DIRE, which in some case, many organizations I worked with were in dire need of a different perspective, which this set of pillars set out to accomplish. First and foremost, not every company is the same or is in dire need of this perspective. However, I found that as companies and networks evolve, there are always opportunities to revisit the pillars to ensure a strong foundation for NetOps moving forward. In the next few sections, I'll dive a little deeper into each pillar, primarily focusing on the more prevalent needs and challenges that I've come across. This is by no means an exhaustive look into the pillars. However, the purpose is to raise awareness, which will lead to your own application across your NetOps organization and help to improve what you're doing today.